Alright, so today I would like to go over a problem that kind of got to me. I had an interview recently and I had to solve a variation of the Max Subarray problem, and I didn't understand or know the different speed complexities in terms of the ways you can solve that problem, and that kind of hurt. So I've studied it and I wanted to share that knowledge. I'm going to use this video to share that knowledge. Also, for some back knowledge and just to get a grasp of everything that's going on, at least for that problem, I'm going to briefly cover Big O and the difference between divide and conquer and dynamic programming. Not in depth, but enough to get the general gist. With that said, let's get it. Alright, so first and foremost, we should probably figure out what the Max Subarray problem is. And for that, there's always Wikipedia. Wikipedia comes through. So according to their words, in computer science, the maximum sum subarray problem is the task of finding a continuous subarray with the largest sum within a given one-dimensional array. An array being just a list of numbers. And then if you go from here, they give you the formal math definition, but we don't really care about that. That's not really important to us. So going to their example. So for example, for the array of values, and they give you a list of numbers, -2, 1, -3, 4, -1, 2, 1, -5, 4. The contiguous subarray with the largest sum is from this index to this index. So 4, -1, 2, 1, with the sum of 6. So more or less, if you're thinking about this problem and you want to have it like concrete in your mind, somebody's going to give you an input of a list of numbers, positive and negative, and you have to decide from that list of numbers at what point from the start index to the end index is the maximum subarray or like subset that gives you the largest sum. And from here, in this one, it was from this 4 to this 1. This problem does carry a number of caveats or properties that you should be aware of. Mainly scenarios where this problem doesn't make sense. That's what it sums down to. So the first one is if the array contains all non-negative numbers, as in your array is just has positive numbers in it, then the entire array is always going to be your answer, because since you're never going zeros or negatives at any point in time, your summation is always going to grow, and thus all of your numbers together are going to be the greatest sum. Another caveat is if you have no positive numbers at all, and all you have are zeros and -1s, and they cover that here in this point. I can just summarize. You can read it, but I can summarize. In summary, it's if you have 0 positive numbers, then your summation can only stay at 0 or become less. At that point, within your array of numbers, the number that is the greatest in your array, that number by itself is going to be your maximum, like your maximum subset. For an explicit concrete example, if you had the numbers 0, -1, -2, -3, regardless of how you go about trying to divide it into like subcategories, 0 is going to be the greatest number in that group, and 0, regardless of where it's placed, is going to be your maximum subarray. Because if you add any of the other numbers, you're going to go down and make the number negative. And then the third property, which is something you should just be aware of, is when you're solving problems like this, there could be multiple correct solutions. As in, you could have an array that's large enough and has enough numbers and situated in such a way that let's say the greatest sum was 6, right? You can have a subarray in the front that says the greatest sum is 6, and you can have a subarray all the way in the back that also sums to 6. Now, given that both of these sum to 6, then they're both correct. So be aware of that. Alright, so moving on. This problem can be solved using several different algorithmic techniques, including brute force, divide and conquer, and dynamic programming. And I say and dynamic programming, and I skipped this section because I don't know what this really means. They have reduction to shortest paths. I don't know how to interpret that. And somebody said they need a citation, so I'm not sure they know how to interpret it either. But it's here, and that might be a possibility. However, for this video, we're going to go over the brute force method, the divide and conquer, and dynamic programming. So, real quick, what is brute force? Brute force typically means that you look at every possible combination, and then from there you devise how you're going to, or you pick out what the answer is. So in terms of a subarray of this, right? You're going to look at every possible subarray and then just compare and contrast until you come out with the greatest or the maximum subarray. Divide and conquer, we covered in the regression video, but just to do a quick recap, divide and conquer is your ability to take a problem and divide that into subproblems that are very distinct, and you can keep subdividing these problems into subproblems, and by solving these subproblems you eventually get to an answer for the entire problem. But note that these problems are distinct from each other. The reason why I emphasize the distinctness of it is because dynamic programming more or less has the same definition as that divide and conquer, with the distinction of the subproblems are overlapping, as in solving these subproblems brings you closer to the actual answer. Can I give an example of that? Alright, yeah, so if I go to the page, I have dynamic programming opening. One example that they give is Fibonacci sequence, right? And we know the regular Fibonacci sequence, we covered it, we did a video on it. We just have the definition. Fib of n is equal to fib of n minus 1 plus fib of n minus 2, right? This recursive call. In terms of their example of dynamic programming, they did what we did in, I guess, our last video when we added a dictionary memorization. If you have a dictionary lookup, they did it right here. They have a dictionary, here's the function, and then they're looking up possible values, or possible already calculated values in this dictionary. So basically, what this sums down to is they realize Fibonacci can be broken into subproblems, just because it's defined recursively, so it meets that criteria immediately. They also realize that if you save or store your answers from the previous subproblems into a dictionary, then they could just be used incrementally to solve the actual problem. And every time you put one of those answers into a dictionary, at least in this case, it gets you closer and closer solving to the actual problem that you're about to receive. And you're not exactly solving subproblems in isolation anymore. So that's a very loose description of why divide and conquer and dynamic programming are different. Personally, I'm not sure if the difference is all that important. Just being able to solve the problem is important. But yeah, let's go back to maximum subarray. One of the things I found interesting, at least going through the Wikipedia page on the problem, is that Wikipedia, just in general, gives you some history to the problem and the people, the situation surrounding the problem. So, from a historical context, the maximum subarray problem was proposed by Elf Grenadier in 1977 as a simplified model for maximum likelihood estimation of patterns in digitized images. Okay. Grenadier was looking to find a rectangular subarray with maximum sum in a two-dimensional array of real numbers. And for some context of what that actually means. So I have a pen now, and he has a rectangle, right? Because he's doing a matrix. So he has, these lines all represent arrays, and it's a two-dimensional array. this person wants to be able to find a rectangle within here that has the maximum sum, like in terms of the rectangle itself. So let's say, for example, it's this thing. From here, I don't know, here, here, and here. In order to figure this out, he has to solve the individual problems of knowing what are the, I guess maybe even the list of maximum subarrays in all of these lines, going across and down. Since he knew that was a big part of solving this problem overall, he was able to abstract that out and ask that question independently. So picking up from here, based on what I was saying, Grenadier proposed the one-dimensional problem, which is the problem that we're looking at, what this page is dedicated to gain insight into its structure, the structure of the problem that he wanted to solve, the 2D one. And then from here on, it's going to start talking with reference to Big O, and we actually haven't covered that yet, so let's go over that real quick, just a brief overview. So here's the Wikipedia page on Big O, and though they have a general definition, it's going to be more practical for us just to read the computer science definition. In computer science, Big O notation is used to classify algorithms according to how their runtime or space requirement to grow as the input size grows. So breaking down this sentence, more or less, an algorithm, which I did not mean to click on, an algorithm is just your sequence of events that you're using to get your work done and reach a solution, right? Big O is measuring how different inputs affect the runtime, how long your program needs to run for, your algorithm needs to run for, and at times space requirements, as in as the input grows that's being put into your algorithm, how does the amount of space your algorithm take up also grow? Like those two correlations. And when we talk about correlations in computer science or just programming in general and runtime, we think about charts. Like we map Big O to runtime complexities in charts, and this is an example of that. So in this chart, n more or less represents the input, right? Alright, for the sake of argument, we can say that n is an array of n numbers. So if you're Big O of 1, what that means is that if your algorithm took in this array that is of length n, the only thing you needed to do in order to solve your problem or to reach a result was to look at one specific placeholder, one index in that array, and then you were done, you returned. A lot of times that's seen or thought of as lookup tables and possibly a dictionary. So let's say you had a dictionary and it was already populated. If you want to look something up, it's thought of as one operation, and thus Big O of 1. And when I click on this, it grows. Alright, so Big O of log of n. Log of n, at least to my knowledge in computer science, is typically log base 2 of n. So we're thinking about dividing things over and over and over again by 2, hence binary search and binary trees and things like that. Anyway, what this means, at least to me, is that you have an array of length n again, and in order to reach a solution, like the processes that you're going through, you are continuously dividing the subarray by 2 and then operating on whatever is at that index. And because you're continually subdividing it by 2, it maps out to the mathematical property of log, and thus we have log of n, where n is the length of the array. So for Big O of n, going back to the same example, we have an array, length n. This means in terms of operations, we more or less had to iterate over each element within that array. Just a straight iteration. Big O of n log n is, well, let's take a step back. Big O properties adhere to multiplication properties. So it's equivalent to Big O of n here times Big O of n, Big O of log n. So this thing here. So what that means is you both had to iterate over the array of n elements, and then post that you had to do something that subdivided that array by seemingly 2 continuously. And after doing those 2 processes, you were able to reach your conclusion or your answer. And then coming to n squared, like big O of n squared, what that typically means is that you had your array of n elements, and then for each element in that array, you've iterated over the entire array. So it sort of makes a grid or a square, depending on the way you want to view it. I'm not really going to explain these 2 because they don't really matter in a lot of cases, but again, this is how many operations you're doing, and this is how many operations you need to do with reference to n in order to complete the task. And this chart is supposed to show over time how slow or fast your program will run. And fast being this green area, this yellow area, and slow being, as the input size grows, this stuff. This red area, quote unquote, horrible, at least according to this chart. Alright, so now that we have that overview, let's go back to the maximum subarray. So Grenadier himself derived an algorithm that solves the one-dimensional problem in big O n squared. Time is right here. Which means that he was able to solve this problem by doing for every element in the array, iterating over the entire array, more or less, which equates to the brute force method, which is this one. When Michael Shamos, I might be mispronouncing that, I'm bad with names. When Michael heard about the problem, he overnight devised an big O n log n divide and conquer algorithm for it. So again, this is divide and conquer, but let's step back. It is big O n log n, and what that implies is that this person had to iterate over each element within that array, and then post that, or in the midst of doing that, they don't have to be in order. They subdivided the array seemingly by 2's over and over and over again to get something that was a log of n. And that's how they reached their solution. And that's pretty common in terms of divide and conquer algorithms. You divide your problem seemingly by 2's recursively all the way down, and you use some sort of calculation within that to solve those sub-problems on the way up. Soon after Michael described the one-dimensional problem and its history at a Carnegie Mellon University seminar attended by J. Kadane. I have butchered that name so many times so far that I'm just going to say J. I know I have the last name written down everywhere, but this person's now J to me. So J was at the seminar, and this person designed a big O of n time algorithm, which is as fast as possible. Alright, so let's take a step back and analyze that for a second. J devised a big O of n time algorithm. So what does that mean? So big O of n, like I was describing earlier, is the idea that when you were trying to solve this problem, you more or less just had to iterate over the problem once, as in looking at each element in the array and saying, okay, I'm done after that. And going back to the screenshot, this chart, we can see this was the Grenadier solution. So as n grew, it became sort of hard to solve problems. It was just too slow, runtime. Here is the n log n solution, so the divide and conquer. And as it grew, it was okay. This is usable. I mean, anytime you have an n log n solution, that's pretty good, at least in my book. And then here is the J solution, which was big O of n, and they noted that this is the fastest possible solution. So I want to speak on that for a second. So they said it's as fast as possible, and the reason why they can say that is because if we go back to the original problem, and we just look at this example, in order to find a sum of anything, you have to at least look at the items within the group, right? So in order to not even find the largest summation, to find any summation of all of these numbers, you have to look at each one of these. And because you're looking at each one of these items in the array, at the very least you have to, that is big O of n, because you're going from index 0 to n and you're looking at every element in the array. So as long as this person didn't do anything more than that, for the most part, yeah, there is no solution that is faster. There could be other solutions that are equivalent or equally as fast, but faster? Nah, not really. So that was the general history of the problem. And before I go on to show you the solutions in Rust, I want to note one thing that I thought was very, very interesting. So we talked about Grenadier, we talked about Michael, and we talked about Jay. If you're new to computer science, or I guess new to this problem, you might have the assumption that these people were programmers. You'll be wrong. Well, I mean, wrong in a sense. So Grenadier was a Swedish statistician and professor of applied mathematics. So probably used programming in his everyday life, depending on what years. 1977, possibly. I don't know how prevalent computers were back then. And then let's go to Michael. Oh, I guess I can call him Mike. Is an American mathematician, attorney, book author, journal editor, consultant, and company director. He is the author of computational geometry. More or less, Mike for short, was a math person. So this person did a lot of math and a bunch of other stuff in their lives. This person was a statistician and needed to be able to solve a problem of his. And let's look at Jay. Jay is the university professor of statistics emeritus in the Department of Statistics and Social and Decision Science at Carnegie Mellon University. More or less, these people, all of them, were math people, and two of them explicitly worked in the field of statistics. How this became a computer problem that we now run into all the time in terms of interviews, I have no idea, but I thought that was interesting. Alright, so let's get to the problem. Let's get to the code. Alright, so I've opened my editor and I have the code up, and this is a lot in terms of written stuff, so I'm gonna post it on GitHub as well. So I'll have that link in the description. Anyway, I have a brief description of what the maximum subarray problem is, and I took this from LeetCode because, of course, this is also a LeetCode problem. One thing I did find really interesting, though, in terms of their example is exactly the same as the example in Wikipedia, so I don't know which one came first. And just to verify, you see the -2, 1, -3, and the answer being 4, -1, 2, 1, summation 6. Go back here. Bam. Same exact problem, same exact example. Who knows? But that's not important. Alright, so let's scroll down. Oh, I guess some things, I have notes in here. The notes cover where I got the solutions from. So the brute force one, which is the first one we're going to go over, is pretty straightforward to think about. I wrote that myself. However, the recursive solution, I wasn't able to come up with that myself. Instead, I went to one of my books. I was casually reading and noticed that it's in the Introduction to Algorithms edition, 3rd edition, probably all of these books. They have a complete section dedicated to it and homework problems. So it's prevalent. And then in terms of, again, I'm going to say this person's name is Jay. In terms of Jay's solution, that's on the Wikipedia page, the one that we were just viewing. If you scroll down, it's there. It's written in Python, but it's there. Alright, so continuing onward. So let me go over some of the extra stuff I wrote just to make the solution easier to write. I have a public struct called solution, right? And my solutions, what I care about is the start index, the end index, and the summation, like the sum of all the elements within those points. I made that into its own struct because it makes it easier to write and follow through with everything else. Clarity. And best practice, at least best practices that I know of, I created a new function so I can easily create my solution struct. So the brute force solution. Here it is. It's not all that long. I'm taking in an array of numbers, well, a slice of I32s. This is syntax for a slice if you aren't aware. Have the and symbol, and then the type within the brackets. And then I'm returning an option that holds a solution. The reason why I'm returning an option is because if the array is 0, like the length of it is 0, as in there are no elements in it, then you need to return none. There is no real solution. And I wanted to have that incorporated in my answer. So yeah. Coming down to the first line, this is a habit of mine. I like to note where my result is going to be. So I create a result mutable, set it to none. Let mutable sum equal I32 min. So there's some history behind that, and I'd like to go over the brute force algorithm first before I get back to that. But I'll explain it. So the idea of brute force is, like I was saying earlier, looking at every possible subarray and then keeping note of which one is the greatest. So the way we go about doing that is we have to do a double iteration, as in a nested for loop. So we do for, I have start in 0 to the length of the array. So iterating, like getting my first iteration ready. Within here I have the current sum because I have to keep track of the current sum. And at any point in time, if the current sum is greater than the best sum that we know of, then we have to switch it out, but we'll get there. So for the second iteration, I have the end. In start, array.length. Actually, I'm going to write it out so it's a little bit clearer. Let me switch screens. So the brute force solution, as we already discussed, is big O of n squared. And we already discussed that big O of n squared is like taking an array and iterating over it, like for each element iterating over the entire array. So for 1, 2, 3, 4, 5, 6, 7, that was a little bigger. Let me make a smaller example. Let's do 3. 1, 2, and 3. In terms of operations, it kind of looks like a grid. As in, the first element's going to go iterate over it, the second element's going to go iterate over it, the third element's going to iterate over it, and you kind of get just this 3, which is n squared. And in terms of operations, right? 9. So in this case, it is important to note that 1, big O of n squared, our big O notation in computer science is it's a rough estimation, so it's not always exactly that. But anyway, for our array, let's say we have this many items in it. 1, 2, 3, 4, 5, 6, 7. There, n equals 7. Do it other way. N equals 7. We're going to, the way the for loop is written, we're going to have our start. And we're picking index to start with. And then for each index, we're going to iterate over all the ones that are following it. So for the first one, we're going to look at U, 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 and U. I guess U included. But on the second pass, we need to move things over. So let's draw this again. Our start is now going to be over here, and we're going to look at these. And do it one more time for example purposes. Our start is going to be here. Let me close this door because the cat just walked in. Our start is going to be here, and we're going to look at these values. And the reason why we're looking at these values and we're looking at them individually is because we want to know what the subarrays are, right? So this by itself is a sub. These two together are a sub. I can just shade them in. But these three together are a sub. All the way down. And we're keeping note of what the current summation is, and if that current is greater than what we consider to be the best summation, or the best result at the time. So this is all the combinations for starting at index 0. So then we increment over, and we're starting at index 1, and we do the same thing over and over and over again, just so we can see all the possible combinations. Alright, so let's go back to the code. So what I was just explaining on the document was the for loops and how they work. And I explained the summation of what we're looking at, right? We're getting the current summation of all of the elements between these two indexes, the start and end. And if the current sum is ever greater than what we believe to be the best sum, then we set the current sum equal to we set the sum equal to the current sum, and then we create a new solution. And if we do this for if we're looking at all possible combinations, then we're always going to come out with the result, a correct result at the end. And we just return that. That's brute force, and big O n squared. Grenadier knew how to do this. Alright, moving down to the divide and conquer. So the divide and conquer, which I got from the algorithms book, is a little subtle in terms of the way they broke down the problem, and a little unique in terms of what they thought about the problem. So before I go through the code per se, I want to go over their ideology. Alright, so we're going through the same problem, right? We can have all of these different boxes. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 8, right? N equals 8 in this case. What they noted is that if you're going to have a maximum subarray, then it can exist. Let me break this in half. 1, 2, 3, 4. Here's the midpoint. That maximum subarray can exist on the left side, as in within these bounds. It can exist on the right side, as in within these bounds. Or it can exist somewhere in the crossing. So crossing, I'm going to call it slash mid, which means that it exists on the left side, but it crosses over the middle, and it also exists on the right side. So those are your three possible solutions, or three possible places that a solution could exist. So if you want to, another way of going about solving this problem is to note that if you can find the maximum subarray on the left, and you can find the maximum subarray on the right, and you can find the maximum subarray that crosses over the middle, you can compare those three solutions, and whichever one is greater is going to be your final solution, or the actual solution for the maximum for the entire array. So that's the way they thought about the problem. Now, given that they were able to subdivide it in the middle, we can break this up into subproblems. So let's look at the left side. So bring it down here. We now have 4. 1, 2, 3, 4. I guess this is 5. 1, 2, 3, 4. N equals 4. This problem looks exactly like that problem, with the difference of n is smaller. So we can break this down in the middle. We now have a left, we now have a right, we now have a mid slash crossing, and the same logic applies. And then you can do it again. The same exact thing happens on the right side, so now you have the left side and you have the right side. So that's the logic of how this plays out. The way they actually go about doing the calculations for like the summation for the midpoint is kind of unique. So they take a point, and we can look at this example. They take a point to choose to start from, and they're going to look from this point spanning out leftward to find out what the maximum subarray is here. So let's say that goes all the way to these three. Let's just color them in, right? Then they're going to look at this point again, and this time they're going to expand out from the right. And let's say that only covers these two. So in doing this, they're going to note what the leftmost point is, this point. I just circle it. And they're going to note what the rightmost point is. And then in terms of the solution, their index is going to be, the start point is going to be the leftmost. So leftmost. Their end position is going to be the rightmost. And then their sum is going to be equal to the left sum plus the right sum. So left sum plus the right sum. And it turns out if you do that, oh, my handwriting is really bad. My apologies. I hope the words were clear. But yeah, anyway, it turns out if you do that, you can do that recursively for all of these subproblems, and then you get the answer to everything. So let's go through the code real quick. So starting from the top of divide and conquer, some things are a little bit different in terms of our inputs. We still have our array, which is a slice of I32. Low, low and high, though that naming convention came from the book. I just kind of copied it. It could just be start index and end index. But that's what it means, start index and end index. So when you start the problem, your low is going to be 0, and when you start the problem for high, your high is going to be the length of the array minus 1, because you don't want to have that issue. Anyway, we're going to return an option that contains a solution. So like I was saying before, the edge case, if the array is empty, return none. Alright, let's get to the meat and potatoes of the problem. So if high and low are ever equal to each other, as in if your start index and your end index are ever the same, that means you only have one element in your array, right? And if that is true, you can just return your solution, where your start index is going to be your low index, your end index is going to be a high index, which in this case they're both the same, and then your summation is just going to be the element at the index of low or high, because the indexes are the same. So in the case that this is not true, as in if your high index, well, if high and low are not equal to each other, that means that you have more than one element in your array. Alright, if you have more than one element, you can find a midpoint. Midpoint, low plus high divided by 2. So we're doing the subdivide by 2, which more or less gives us that log n feel. And then here's what I was talking about for the sides. Here is the left side, here is the right side, and here is the middle result, right? So divide and conquer, recursively calling, all on the left. And this is going to go down the stack recursively and then come back up. And it's going to give us the result of the maximum subarray for the left side. Same thing happens on the right. Right result is equal to divide and conquer. One thing I forgot to note, I should have pointed out. So the left side, you can see the indices have changed. So the left side goes from low to mid, and that encompasses the left side. The right side, which still does the divide and conquer, go all the way down, all the way up, is going to have the indices from the mid plus 1 to high, which is the right side. And when these resolve, it's going to have the right side is going to have the maximum subarray for the right side. And then we look at the middle. So the middle is not a recursive call. The middle is find max crossing subarray. And it's going to take in the array, it's going to take in the low, it's going to take in the mid, it's going to take in the high. So the find max crossing subarray method or function in this case, is what I was describing in terms of the spanning from the middle to the left, middle to the right, and then figuring out what the summation is, or the greatest maximum summation for that point. And we can go to that real quick. That is here. I'll make it a little bit smaller so it all fits on the screen. So find max crossing subarray. Array takes in the slice I32, we have low, we have mid, we have high, and we know what those points are. The I32 min, which I just recalling that I forgot to explain, it's I32 min is the minimum value of the I32 span, as in it's the lowest possible value that can exist. The reason why we need that, and I can go back up here so you can see it here as well. The reason that we need that is because when we're trying to figure out if the current sum is greater than the best sum, for the first case, first iteration, we don't have a concept of what the sum is. So in terms of books, a lot of them depict that initial sum as negative infinity because everything is greater than negative infinity. However, in terms of computers, we don't really have a negative infinity in a lot of cases. So the next best thing is using the smallest possible number that exists. And that is the reason why we have I32 min. Come back here. We have that here as well, and we use it also for the right side. So we initialize the left sum to quote-unquote negative infinity. Sum is going to be 0. Max left, which is the indices point, is we're going to start off at 0. And then we do the for loop, right? And if you note, this is the index, but the range is from low to mid, and then we reversed it. As in, we're looking from mid, and we're moving left to lower. And then we do the summation. We take the sum, and if that sum is greater than what we believe to be the current best left sum, we set the current left best sum to that sum. And then we note the index. That same logic applies to the right side. So we have the right sum, we have it set to quote-unquote negative infinity, sum equal to 0, let mutable right, as in the max right, this is the index. Then we have the for loop. This for loop is not reversed. It goes from mid plus 1 to high, right? The reason why this is not reversed is because we're moving to the right side. So that's the direction that we want to go to, and that is correct. But the logic itself within this for loop is exactly the same. We're taking the current sum, which I just called sum, and we're checking to see if it's greater than what we know to be the best right sum. And if it is, we reset the best right sum and we note that index. And then in terms of return, we return the left index, we return the right index, and then the sum, which is the left side plus the right side, is returned. So let's go back here. Once these go down the stack and up the stack, we then have the best solution for the left, best solution for the right, and best solution for the middle in all of these cases. And we get to check to see if the left side is greater than the right side and the middle portion. If it is, return the left, because that means, or that implies, that the maximum subarray exists on the left half of the array. Do the same check for the right side. If the right sum is greater than the left sum, and the right sum is also greater than the middle sum, then the solution exists on the right half of the array. And if those two are not true, then the answer must be in the middle portion of the array. And that is the divide and conquer portion of how to, the divide and conquer solution of how to solve this problem. Alright, so the next portion, oh, one thing to note, this is n log n, seemingly because the log n from the divide and conquer, but in the maximum crossing subarray portion, we are iterating over the array, and I believe that portion, the find max crossing subarray, is where we get the n from in the big O notation. Alright, moving on to J's algorithm. So for J's algorithm, it's kind of described in the Wikipedia page, so I like to go there first. J got his own section. J's algorithm scans the given array from left to right. In the jth step, it computes the subarray with the largest sum ending at j. This sum is maintained in variable current sum. Moreover, it computes the subarray with the largest sum anywhere in the array A from 1 to j, maintained in the variable best sum, and easily obtained as the maximum of all values of current sum seen so far. So from that point, let's go back and just analyze what they actually said here. So we know this is big O of n, just because, well, I told you that, but it is. Actually, no, the article mentioned that. So we know this is big O of n, right? That implies that we iterated over the list from list be having n items in it, going from the start 0 to the end. What they're stating here is that the jth element, given that j is somewhere between 1 and n, it computes the subarray with the largest sum ending at j. The j sum is maintained in a variable called current sum. So while we're iterating from left to right, we are taking note of what the current sum is. And it computes the subarray with the largest sum anywhere in A from 1 to j, maintained in a variable called best sum. So while we're iterating over this thing, we're keeping note of what the current sum is. And all of the current sums that we've seen, out of them, we're noting what the best sum of that is as well. And we're saving that in best sum. So, alright, I'm going to skip this portion because this just looks confusing. But they have the answer written out in Python. And there's some things to note when we're looking at this real quick. We should note that, 1, this solution doesn't take into account the start index and end index. They have that written down here. But 2, we should note that this solution assumes that the lowest summation possible is 0. So our solution has to be modified for that. And they note that in this description, but this description is really wordy with notation. Anyway, we start off with a list of numbers. They note that the best sum is 0. In our case, it's going to be negative infinity. It's a kind of note here. They note that the current sum is 0, which makes sense. And then while we're iterating over the numbers, we're always checking to see if the current sum plus x is greater than or equal to the lowest possible number. In this case, it's 0. If it is greater than that, we're setting that to current sum. If it is less than that, then we're resetting the current sum and starting over again. And then for this line, they're checking to see whether the current sum is greater than or equal to the best sum. So if the current sum is greater than the best sum that we know of, then we're setting that to the best sum. If it is not, then we are keeping the best sum. And then here they're just returning the best sum that they've seen. So this is pretty straightforward in terms of implementation. one thing I would like to note, this is called dynamic programming, seemingly because while we're going through these, actually I think it was more explicit up here. So while we're going through 1 to j, right? J being somewhere less than n or somewhere in between. At every point in time, we are capturing the best solution at that point. And though this is considered a subproblem, while j grows, those subproblems are not distinct. They're all helping each other get to the end solution. At least that's my take on it. I could be wrong. Anyway, on Wikipedia they also have an example written in Python of how you keep the indices, which I wrote out in Rust, and then I also modified it so that it doesn't assume that the lowest answer for best sum is 0. So let's go to the code. So we take an array, it's a slice of i32s, option, return to solution. Like we were doing before, we set the best sum to be negative infinity, because we need to start somewhere. Best start, as in the best start index, we're going to set it equal to 0 for now. Best end index, we're going to set that equal to 0 for now. Current start index, we're going to set that equal to 0 for now. And the current sum, we're going to set equal to 0 for now. So these are just placeholders for the most part. Go with the edge case. If the array is empty, return none. And then in terms of the iteration, so we have one for loop, and we have the current end and x. So current end is going to be an index, and x is going to be the value that's it from the array. The way we go about doing this is we're iterating over the array and we're using enumerate. Enumerate allows us to have the index of the element that we're currently looking at, and that's why we have it here. We noted it as current end. So if the current sum plus x is less than or equal to x, then we want to restart things. So this is equivalent to the line in the Wikipedia article. So let me go back here. It's equivalent to this line, right? Where we want to decide whether or not the current sum needs to start over or we're going to continue adding to it. So our marker for that is if the current sum plus x is less than or equal to x, then we have a possibility of a new summation that's going to be greater than the one we're looking at. And as such, we should start over. So when we start over, we note that the current n, we're going to set the start to our current n, or the place that we're at right now. And we're going to set the summation equal to x. As when we're starting all over again, everything that you already captured can be erased. If this is not true, as in the current sum plus x is greater than x, we come down to the else case. We add on x to the summation, and then we check to see if the current sum is greater than the best sum that we've seen so far. If it is, then we have to reevaluate our best sum. So we set our best sum equal to the current sum. And then we also change the starts and end. So the best start is going to equal to the current start, and the best end is going to equal to the current end. And after all of that, we just return a solution that is best start, best end, best sum. And that is the end. So those are the three solutions. And I think it would be pretty irresponsible for me if I wrote these up and then test them. So we have our test cases. So going about the test cases, let me first walk over some of my thoughts on how I went about doing this. The brute force, divide and conquer, and J algorithm solve the same problem. So in terms of test cases, they should probably go over the same test cases. They'll all have the same test cases and return the same result. In terms of correctness, that makes sense. Also in terms of correctness, or at least debugging, for me, it is easiest to debug something I'm most familiar with, or the easiest one to understand, and that's brute force. So I can guarantee that the brute force one is right pretty easily, at least personally just going through it. In terms of divide and conquer and J's algorithm, if something were to go wrong there, it's a little iffy on how much or how long it would take me to fix it. So what I did was, given that I can assure that the brute force is correct, as long as divide and conquer and J's algorithm give me the same answer as the brute force, then in tandem, that means I can ensure that the divide and conquer and J's algorithm are also correct, at least in terms of the way I've implemented them. So that's the approach I took. Some things to go over real quickly. I created a struct for my test cases. I have the input, which is a vector of I32s, and in my struct I also have the expected solution, and solution is still the same solution struct, so it has the start index, the end index, and the sum. I have a new method to help instantiate or create my test cases. But coming down here, I have a function that has my test cases in them, so that this just ensures that I can give all of my my tests the same test cases. So write it here and then call them in the actual test functions. So I have my vector. I have my first test case, which I have the array here, and I have my solution here. And as you can see from the solution, this is the solution from start index 0, end index 2, summation 6. Meaning that the answer is, the Max Subarray exists on the left side. So left side covered. For the second one, we can look at the solution, start index 6, end index 7, summation 7. That's right here. This means that this test case covers when the solution or the answer is on the right side and only on the right side. And then down here, for the third one, I have 2 to 4 and summation is equal to 9. So 0, 1, 2. So it starts on the left side and it crosses over the middle and it ends on the right side. So this test case goes over the case of when the solution exists in the cross left to right of the array. And then I have an extra test case, which I think is just more or less a duplicate. Doesn't really need to be here, but the more the merrier, right? Anyway, here it is. Brute force. For the brute force test case, this is how I wrote it out. My normal cases, for case and get test cases, so I can just iterate over them. I can say result equals to brute force, pass in the test case. Then I can assert that the result is equal to the expected result, so case.expected. And then for each of my test cases, because they all have the same layout, I also have the edge case of when the array is empty. So I create an empty vector, I assert that it equals to none, and then I pass in the empty vector into the algorithm. And I did that for brute force, divide and conquer, and J. So now that it's there, let me run the test just to show y'all and prove to myself as well that everything is working as expected. So just create another one of these. Cargo, test, and what file is this? I don't want to run all of my tests. Let me run all of my tests. There's other stuff here, but what we care about is the maximum subarray. So control copy. Let's clear this and then just run the test for that one problem. Cargo, test. So we ran the 3 tests. Brute force is okay, J is doing well, and so is divide and conquer. Alright, so at this point in time, we went over the problem. we went over the solutions, and we talked about roughly the time complexity, or the big O, of these solutions. One thing I really care about in terms of like theoretical answers and actual answers is taking benchmarks, or like evaluating if the theoretical is actually true. So in doing so, I also created benchmarks for these. So let me go to that real quick. Quit out of here. Bench. So I use Crazcalm, which we covered, and I created benchmarks that compare these three algorithms with different inputs. And as we know, for big N, or for big O, the input is N, and as N grows, we want to see how that affects the time complexity of how long these algorithms take to run. So let's go over this real quick. I'm going to cover format in a second, but we have Crazcalm, I have random here, and I'm importing this from, it has to be public, so I'm importing this from the crate in order to use it here. Anyway, for Crazcalm, one of the things I noticed is that if you want to have a, let me find, oh, here's an example. If you want to run a test with an input, then you kind of need to have a new name, and anything you pass into like the benchmark ID new has to implement format. And because of that, I had to create a wrapper around my input. So I wasn't just passing arrays in, because vectors implement debug, but they don't implement print. So I had to do that for they don't implement display. That's what it was. So I had to do that for myself. So coming back up here, I have my struct, make sure I had debug, clone. I think I needed clone, I'm not exactly sure, but debug, I think I definitely needed. It just holds a vector of I32. I have a new function to create it, to instantiate it, I mean. And then here I have a method that I'm using to create my test cases, my array of length ends. And I'm taking in size, which is going to be, I guess in this case, N, if you're thinking about it in terms of big O. I am starting off my random number generator. I'm creating a vector that has the capacity of size N. And then I am filling up that vector with random I32 values. So it's more to note that for benchmark, you're not testing correctness, because correctness is done in your unit test, but now you're testing how long it takes to complete a process. Alright, so yeah, I'm creating my vector and filling it up with random numbers, I32s, from 0 to size, which you can think of as N. And then I'm returning that as the data. And then I implemented display for data. Given that Crazcalm wants to print out the things that you passed into it, originally I was printing out all of the items within the array, which is silly when you have arrays of, like, I have it down here, 10, 100, 1,000, 10,000. There's no point. So instead, I make sure it prints out the length of the array. So vec of length, and then just put the length there. So coming to the benchmarks. So for Crazcalm, you have to create your own benchmark function that takes in C, mutable Crazcalm. I have my cases, my case of 10, my case of 100, my case of 1,000, my case of 10,000. And then I have my for loop here, which is iterating over these cases. So for each case, I want to take these actions to benchmark it. I'm creating a group allowing, so from the general gist I'm getting, a group allows you to compare directly multiple functions or implementations. So creating a group, calling it Max Subarray Solutions. And then for the first person in the group, I'm putting in the brute force algorithm. So bench with input. And the input is going to be the case. So I'm cloning the case so I can pass it into this thing. I'm also giving it a reference to case. And then in the benchmark function that group needs, I have a closure, and I'm doing what they suggest. I'm doing the benchmark iter, and I have the function in here, another closure, and it's doing brute force, and I'm passing in the data. So a reference to data vect, then to an actual vector, and then make it into a slice. There may have been a better way of doing it, I'm not sure. But that's the way it ended up working for me. Alright, so I did the same thing for divide and conquer. So that's here. Case clone, yada yada yada, same exact steps. And divide and conquer, as you remember, or know, it takes in different inputs than the other two. It takes in the array, then it takes in low, which is 0, then it takes in high, which is the length of the vector minus 1. And I casted it to usize, but I'm not even sure if that was needed. It might have been done implicitly for me. And then lastly, J's algorithm, same thing, benchmark, new J, clone the case, pass it into here, calling J, passing the array. And for criterion, these two macros seem to be mandatory when you do things. Alright, so let's run this and see how fast they are in comparison to each other. Cargo bench. Let me spell that correctly. Alright, so the benchmarks just finished running. So let's go all the way back to the top. Start taking a look at this. Here we go. Bring that to the top. So we have Max Subarray Solutions, which is the group name I gave them. Brute force vector of length 10. So brute force took 118 nanoseconds. Okay, not too bad, not too shabby. The divide and conquer for vector length 10 took 204 nanoseconds. And this change thing, just so you're aware of it, I've run this benchmark a number of times. It's comparing this result to a previous result, and apparently it slowed down this time. I'm not exactly sure what that is due to. It could be a number of things. Like, things are running on my computer, so the processing time for things is not always going to be the same or consistent. But yeah, in this scenario where we ran it just now, the divide and conquer took 204 nanoseconds. So if you remember that the runtime of divide and conquer is big O n log n, right? And the runtime of brute force is big O n squared. So let's go back to the chart real quick, just to refresh our memories. What we should be seeing is that the big O n log n should run faster than the big O n squared. Like, at no point in this chart does it show that the reverse to be true. However, in terms of practicality or actuality, it all depends on the size of n. So coming back here, if n is as small as 10 items, then yeah, the brute force might run faster than the divide and conquer algorithm. It happens. As we go to J's algorithm, bring that. J's algorithm for length of 10, 35 nanoseconds. 35 nanoseconds. Fast. And this is even in a regress state, so it was faster before. Anyway, 35 nanoseconds blows the other two out of the water. Right? This is 118, this is 204, this is 35. Go on to the next case. In this case, we see that the brute force of a vector of length 100, n being 100, is 8 US, and I believe that's microseconds. And to give you some context, microseconds. Oh, I have specific numbers in here. Let me change that. 1 microsecond. 1 microsecond is equal to 1,000 nanoseconds. So we've now just increased by a unit of measure of 1,000 in terms of the way we're viewing this. Just to put things in context. So this is 8 microseconds. It's really 8,000 nanoseconds. So yeah, brute force of length 100, 8 microseconds. Divide and conquer of length 100, 2 microseconds. Jay's algorithm, 114 nanoseconds. So already at 100, J is a factor of 10 faster than the other two algorithms. But to sort of emphasize the difference between at least the big O n log n and the big O n squared, we can see that here. So the brute force, as we just noted, is 8 microseconds, right? Which is a lot slower than the big O of the divide and conquer, which is at 2 microseconds. This shows that as n grew, the runtime for the brute force became larger and larger at a faster rate than the runtime for the divide and conquer, that's what we expect to happen. So yeah, as n grows, things change. And then Jay's algorithm, Jay's just fast. Alright, so coming down to the next case, brute force of vect of 1,000 elements. This is now at 768 microseconds. That grew kind of fast. So if you remember previously, what was it? For 100 it was 8. So we now went from 8 to 768. Okay. For the divide and conquer, it's currently at 26 microseconds for an array of 1,000. And previously, what was that, 2? Yeah, right here. 2 for 100. So that growth is not as fast or alarming as the brute force one. And then we have J. J is currently at 1 microsecond. As in, 1 microsecond is 1,000 nanoseconds. J is at 1,000 nanoseconds. I'm kind of curious about that growth though. So J also grew by seemingly a factor of 10. But J is just that much faster. Actually, hold on. So if J grew by a factor of 10, what does that tell us? Given that the length of this array is 1,000 and the length of this array is 100, which is a difference of a factor of 10, and the big O of J's algorithm is big O of n, we're actually seeing it grow in tandem with n in the same ratios. So n increased by a factor of 10, so the time it took to solve the problem increased by a factor of 10. That's really cool. That is really cool. Alright, then the last case. So brute force of 10,000 took 76 milliseconds. So we just went up a unit of measure. And let's give you some context for that. 1 millisecond is 1,000 microseconds. 1 millisecond is 1,000 microseconds. And we're at 76 milliseconds. The divide and conquer is still within the unit of microseconds, and it's at 326. So yeah, this is growing kind of beautifully. Like the way the time complexity it's not scary right now. And then J's just chilling. J's at 26 microseconds. So this is the last case, but I want to point out that for J, at 10,000 items, 26 microseconds. If we scroll up to look at the other competitors, when did they hit 26? So Divide and Conquer hit 26 microseconds at 1,000 elements. And did Brute Force hit that? Not exactly. Alright. Yeah. J algorithm is fast. So just a brief recap of what we actually did today. We went over the Max Subarray problem. We looked at some of the history behind it. We looked at all three, at least all three that I know of solutions. The brute force, the divide and conquer, and J's algorithm, which counts as dynamic programming. We ran tests to make sure that the solutions were correct, and then we benchmarked them to see that as n grew, these time complexities did change, so more or less kind of validating the big O notation that we follow. And with that, we have reached the end of the video. If you liked the video, hit like, subscribe. Outside of that, see you next time. Peace.